In this video, we're going to introduce a very important and very fundamental class of functions, namely linear functions. Let's suppose you decide to take your bicycle for a spin and begin riding it down a straight stretch of road. As long as the path that you're riding your bike down is a straight line, we can identify it with a real number line and therefore associate numerical values to different positions on the road. We can then consider the function that takes as input a moment of time and gives as output the corresponding position of the bicycle at that moment of time. And by observing the bicycle as it moves, we can begin to create a table of values. Now let's suppose that starting at time 0, we record the position of the bicycle every 1 second. And suppose that we notice that at time 0, the position of the bicycle is 0. That 1 second later, at time t equals 1, the position of the bicycle is 2. 1 second after that, at time 2, the position of the bicycle is 4, and so on and so forth. What this particular table of values shows us is that for every fixed change in time, there is a fixed change in the position of the bicycle. Indeed, for every 1 second of time that passes, the position of the bicycle changes by exactly 2 units. If we plot the points in our table on a pair of coordinate axes representing time and position, then we see they're organized in two-dimensional space in a very particular way. Indeed, connecting the dots gives us nothing other than a straight line. And the position function of the bicycle, given the data in our table, is precisely an example of a linear function. If we wanted to express this position function algebraically, then the most natural way to do so would be via the formula s of t equals 2t. These ideas lead us to the general definition of a linear function. In general, we say that a function f, defined on a subset of the real line and taking values in the real line, is linear if it can be written in the special form f of x equals ax plus b, where a and b are fixed constants. We might call that the algebraic definition of a linear function, but there's a geometric definition too. A function is linear if its graph is a straight line. This also explains where linear functions get their name from. Finally, and this is an important conceptual point, we can say that a function is linear if, whenever there is a fixed change in its input, there is always a fixed change in its output, just as with the bicycle as it traveled down the road. Every time the input changed by 1 unit, the output changed by 2 units. Let's try to run with these definitions and explore one fundamental feature that any linear function has. What we're looking at here is the graph of a linear function, and we can tell because it's the graph of a function and it passes the vertical line test, and because the graph has the shape of a straight line. What we're going to do next is mark 2 points on the straight line, any 2 points, such as the 2 points in red shown here. These 2 points will of course correspond to a pair of x values on the horizontal axis, and a corresponding pair of y values on the vertical axis. Now we can ask the question, as we move between the 2 red points on our graph, what distance do we cover in the x direction? That is to say, what is the length of the yellow line segment shown on the screen? And the answer, of course, is x2 minus x1, which we often denote by delta x, where that triangle is the Greek capital letter delta. And this simply refers to a change in the input, a change in x. Likewise, the distance between the 2 red points in the y direction, or the vertical direction, would be y2 minus y1, which we similarly denote by delta y. Once again, the delta x represents a change in x, and the delta y represents the corresponding change in y. What we'll do next is consider the ratio of the change in output to the change in input of this linear function. In other words, we will divide delta y by delta x, or divide y2 minus y1 by x2 minus x1. This quantity is what's known as the slope of the linear function. A remarkable feature of the slope is that it does not depend on our choice of 2 points on the graph of the function. So even if we chose these 2 red points on the graph of the function and computed the corresponding change in output divided by the change in input, we would end up with the exact same number as before. The same would be true if we chose these 2 points on the graph of the function instead and computed the change in output divided by the change in input. No matter which 2 points you choose on the graph of the function, the slope will always be one and the same, and it tells us quite a bit about the behavior of the function. Notice, for instance, that in this picture, since y2 is bigger than y1 and x2 is bigger than x1, both the numerator and the denominator of the slope are positive, and therefore the slope itself is a positive number. On the other hand, if we look at a different linear function with 2 points, x1, y1, and x2, y2 marked on it, then we see that here the denominator of the slope is positive, since x2 is greater than x1, but the numerator of the slope is negative, since y2 is less than y1. And therefore, the slope of this function will be less than 0. And for a function whose graph is a horizontal line, like the one shown here, we see that y1 is actually equal to y2, which makes the numerator of the slope 0, and which therefore makes the slope itself equal to 0. So putting everything together, to compute the slope of a linear function, what we do in general is take any 2 points, x1, y1, and x2, y2, on the graph of that function, and we compute y2 minus y1 divided by x2 minus x1. That is to say, the change in the y values divided by the change in the x values. Notice, by the way, that that's the exact same thing as y1 minus y2 divided by x1 minus x2. So the order in which we subtract doesn't make a difference as long as we subtract in a consistent way. If that slope is a positive number, then what it means geometrically is that the linear function is increasing. It goes up as you scan across the graph from left to right. On the other hand, if the slope is negative, then the function is decreasing. Its graph goes down as you scan across it from left to right. And finally, if the slope turns out to be 0, then it means that the linear function is just a constant function. So its graph is a horizontal line. Moreover, if we return to the algebraic form that any linear function must have, then there's a very easy way to read off the slope. The slope of this general linear function is nothing other than the coefficient of x, which we're here denoting a. If a is very large, then the graph of f will be very steep. On the other hand, if a is very close to 0, then the graph of f will be very shallow. If 2 linear functions, ax plus b and cx plus d, happen to be parallel to one another, meaning that their graphs don't intersect, then it must be the case that their slopes are equal. And conversely, if their slopes are equal, then their graphs must also be parallel. So you can tell whether 2 linear functions are parallel to one another just by checking to see whether they have the same slope. What if, instead of being parallel, our linear functions were perpendicular? What if their graphs meet at a right angle? What can we say about the relationship between their slopes then? Well, if the slope of f, that's the blue curve, can be written as y over x, so that starting on the blue curve, we can move x units to the right and y units up and get back to the blue curve, then since g is perpendicular to f, we can start on the orange curve and move y units to the right and x units down to compute its slope. And it therefore follows that the slope of g must be the negative reciprocal of the slope of f. So, if the slopes of 2 linear functions are negative reciprocals of one another, then it must mean that the graphs of those functions are perpendicular. There are many more things to say about linear functions, which we don't have time to address in this video. But one final conceptual point I'll leave you with is the idea that linear functions have a constant rate of change. Indeed, the slope of a linear function can be interpreted as the rate at which that function is changing. And linear functions happen to be precisely those functions whose rate of change is constant.